No, I was 8. Actually, I might have been younger. No, but I'm stuck there.
All right, you ready? I want to finish my cooking. Okay, I'll give you your test back at the end of the hour. You all know your grade, right? Oh God, yeah.
Yeah, it was bad.
Come by and visit me.
I need to.
For 10 and 21, right?
Yep. Is it not working?
I think I got the
I
pressed this and it registered.
Okay, you're aiming for this, Jessica.
It works now.
Okay, okay, cool. Don't ask me. Maybe those physical science kids do something to it.
Exactly.
All right, is there 20 of you? How many are there?
I know it now.
6, 10, 13, 17, 20. Well, we did a whole lot better than we did last class, didn't we? Anybody recognize
I
it?
knew that was the same thing. We were just being quiet. Taylor never listens to you.
Well, I mean, you probably should.
Right? Tertiary. Tertiary.
I really want to get that part back today.
Oh, I forgot. Some of these are dark.
She's like, out my boat.
Long story on the dark.
And I was like, you want a shirt?
Okay, so we've talked a lot about free radicals, right? Because that's the main intermediate in the reaction that we were studying. There are other kind of intermediates that we can have, okay? One is called a carbocation. Carbocations have a plus charge on a carbon. This is going to be an intermediate. This carbon only has 6 electrons around it, okay? So it's real reactive. It's not like you're going to have a bottle of carbocation, okay? You can't. It does something and changes, okay? They're also called carbenium ions or carbonium ions. The one I've seen the most is carbocation, to be truly honest. But this would probably be the second one I've seen the most, second most. Okay, the carbon is sp2 hybridized just like a free radical carbon. And the p orbital, though, in a free radical, it has 1 electron in it. Here it is empty. So it is an electrophile. That means electron loving. Electrons are going to go to it. Okay, electrons will go to carbocations. Okay, this is looking down from the top, and this picture over here, it's sideways, and this is the empty p orbital right here, aka vacant p orbital. We will be using them as intermediates in reactions. Okay, carbocation stability parallels free radical stability. The more highly substituted are more stable. All right, hang on. I think to get this to go away, I have to do that. Okay, so here we have what kind of carbocation is that first one? Jeez. Difficult to write one. A tertiary one, right? Because there's 3 R groups. If you have 2 R groups, it's secondary. And if you have 1, it's, what if you don't have any? That's right. It's a methyl. It's just a methyl carbocation is what we call it. Okay. So notice the tertiary is more stable than the secondary, than the primary, than the methyl, which is the same as free radicals. The same as free radicals. Okay. So now you know what I'm going to ask you next, don't you? Well, Why? Why is the tertiary more stable? Well, why was the tertiary free radical the most stable? There were two reasons. I think it's on a slide. Yeah, here it is. I was pretty sure it was. Okay. Induction and hyperconjugation. So remember that when you had a free radical, your p orbital had one little electron in there all by its lonesome. It wanted a buddy, okay? So you can stabilize by, through the bonds, okay? Pushing electron density into the part that is electron deficient, okay? And you remember this, the sideways, that's the hyperconjugation. If you have more groups, you're doing it 3 times, 2 times, or just 1 time, or no times, okay? So it's the same thing. Hyperconjugation is the through space, sideways. Induction is through the bonds. Hyperconjugation, induction. You can remember? I try. Okay, now, if you are an unsaturated carbocation, you may be able to be stabilized by resonance. Unsaturated means that you have a double or triple bond. Okay, that double or triple bond has to be next door to the carbon that has the plus on it. Okay, so if you had, for example, that carbocation. See a problem? We can't stabilize that one by resonance because it's too far away. Okay, you have to be right next door so you can do resonance. You see how we got from here to there? Okay, those electrons go over there to make that double bond, and the other carbon now becomes positive. Okay, so the double bond is stabilizing through resonance. Stabilizing through resonance is the best stabilization that there is, whether it's free radical or carbocations or whatever. It's always the best stabilization. It's better than hyperconjugation and induction. So if you can do all 3 of those, it's like super stable, okay? Okay, now, do you see this little picture over here? Okay, remember that's like blending the 2 together. So here, sometimes it's a single bond and sometimes it's a double bond. So you put the slashes for the partial bond. Same thing over here. And then do you see how we get these? Because we're going to keep doing that with other things. But here it's positive, here it's not. Here this one's not, here it is. So it's almost like half and half. Since the 2 resonance forms are identical, it probably would be a half and half. Okay? That picture makes sense again? I mean, we haven't talked about that for a little bit. Okay, put the structures below in order of increasing stability. Do I have 2 more to make a guess? 19. I tried to put every possibility. Did I manage it? If somebody's not working, I'm going to click the button. All right. I have to threaten. Oh, wow. I got 4 answers back. Okay. So first of all, let me ask you this. What does increasing mean? Because sometimes I think people, if you have to write that down, increasing is least to most. All right, so which one out there do you think is the most stable?
Most stable?
Yeah, most stable. B, most. Okay, which one do you think is the least? Which one must be in between? Okay, how did you decide? What kind of carbocation is this? What's this one? What's this one? Okay, so increasing, so least is A, middle is, and most is, all right, so which one is that? All right, people who picked C, did you get it backwards? Yes. Okay, so like literally right, least to most to least, depending on if it's increasing or decreasing, you make yourself get it right. Don't get it wrong because of that. That wasn't meant to be tricky. Uh-huh. No, it wasn't. All right, so here is unsaturated free radicals. I need a skinnier pen. Okay, can be stabilized by resonance. So how would you write the arrows for that? Well, how does it work with free radicals? When we did the reaction, what kind of arrows did we use? Half arrows. Okay, so this free radical and an electron from there are going to make a bond. Okay, what happened to the other electron in this double bond? It goes there. Okay, so just for practice now, draw the arrows on here to show this one going back to this one, which I know your sapling is fond of. Okay, so how would you draw, and then we'll talk about that other picture. The arrows to go back to the original. Make sure that you've got it in your head. This one and one of these will make the double bond. And what happens to the other electron in the double bond over here? It goes to the carbon. Okay, make sure you're using the fish hooks. Okay. All right, so over here, sometimes you have a single bond, sometimes you have a double bond. So you get the little dashed line here and here. Does everybody see that part? And look what they put, partial dots. How can you have partial electrons? You can't. But the electron density is shared by both of those carbons. Okay. Okie dokie. Okay, carbanions are negatively charged carbon intermediates. There are 6 bonding and 2 non-bonding electrons. Okay, they can function as bases because they're negatively charged. They can grab an H+, or nucleophiles. Nucleophiles are electron loving. Okay, so they are, they're not electron loving, they're nucleus loving. Who knows what happened? What?
It's red on
It is?
Yeah.
Good to know. Okay, they donate electrons in a reaction. Remember, as we are drawing arrows for things, we always go high electron density to low electron density, negative to positive. Okay, negative is high electron density, positive is low. Okay, now it's important to see that in carbanions, the carbon is sp3 hybridized because there are 4 sites of electron density. So here would be 1, 2, 3, and your electron pair is 4. That electron pair is not in a p orbital like those other ones, okay? It is in an sp3 hybridized orbital because to keep those 4 sites of electron density, 2 electrons, 1 pair is a site, to keep them as far apart from each other as possible, okay? If you look at the nitrogen on ammonia, okay, it is also sp3 hybridized with a lone pair in an sp3 hybridized orbital, but it's not negatively charged, okay, like our carbon is, okay? So because of that, the stabilities are opposite, okay? So everybody see they're opposite. The least stable is the tertiary. Okay, and the most stable is the methyl. So remember what we said that alkyl groups have been doing. They've been donating electron density to our p orbital that's either empty or has 1 electron in it through induction and hyperconjugation. Okay, so if these things that are on here want to donate electron density and you have electron density, that destabilizes it. That make sense? Okay. So carbanions are opposite. Okay. The tertiary is least stable and the methyl is the most stable. Okay. Okay. Carbanions can function as bases and better nucleophiles than amines because they have a negative charge. They even will remove an H plus from ammonia. So here is a carbanion, okay, and it is grabbing that H plus. We're just doing an acid-base reaction. The electrons in the NH bond end up on the N. So in the end, your nitrogen is negatively charged and your carbon isn't. Okay, so if you just wrote it out without all the little orbitals, it looks like the bottom there. Okay. Okay. We will use them again. Okay, carbenes. Carbenes are carbons with only 6 electrons, but 2 of them are a pair. Okay, they have to be formed just like the other things. You have to make them somehow. We'll learn the ways to make them as we go. But that carbon is sp2 hybridized. Okay, you have 3 sites of electron density. In this case, they're using the dibromo one. So here's a bromine, here's a bromine. So there's 2 electrons here, 2 here, and then over here in this orbital is a pair of electrons. What orbital are those in? They are in an sp2 hybridized orbital because this is sp2 hybridized, and the p orbital is empty. The p orbital is empty, okay? But that carbon doesn't have a charge. It might kind of like free radicals, they kind of feel like they should have a charge, but they don't. Okay, so we've got 4 is the normal valence of carbon, right? Okay, how many unshared electrons are there? There are 2. They're both there. Okay, and how many shared are there? 4. Half of 4 is 2. 4 minus 2 minus 2 is? Okay, so convince yourself of that until you believe it. Okay, some people never believe it. All right, now carbon doesn't want to be that way. It wants to have 8 electrons. So as soon as those are formed, they do something. They react some way. Okay. Okay. Here is forming a carbene. Okay. This uses tribromomethane and a strong base. Sodium hydroxide is strong enough. If I said strong base, you still would probably name that one. Okay, so the OH minus removes this hydrogen. Why can it remove that hydrogen? Why is that hydrogen kind of acidic? Because what are the bromines doing? They're all what? Who? They're all electronegative. So they're pulling electron density away. So that makes this H right here acidic, more acidic than normal. If you just had CH4, sodium hydroxide couldn't pull off that proton. Okay, so when it does that, you end up losing a bromide ion, and that's how you make that carbene. Isn't that wild? Kind of wild. It's real different, very unique. They're real reactive, and they do some special things. They just are introducing them here. Okay, so to review, carbocations have a carbon with a plus charge. They have 6 electrons, okay? And notice the stability. Who's the most stable? Tertiary, then secondary, then primary, then methyl. They are electrophilic, okay? The free radicals, that carbon is also sp2 hybridized, and that little free radical is very reactive. Okay, the stability is parallels the other one. Okay, tertiary, secondary, primary methyl. Carbanions are nucleophilic. They often function as strong bases, and it goes opposite. Okay, methyl carbanion is the most stable, and tertiary is the worst. Okay. Carbenes, there is no such thing as primary, secondary, tertiary. You're just a carbene or you're not one. I know, poor little guy. Okay, and it actually is going to function as both a nucleophile and an electrophile at the same time, which is kind of weird. But we'll talk about that when we get there. Okay, why are tertiary carbocations more stable than all the other ones? Induction and hyperconjugation. What is induction? Through the bonds. What's hyperconjugation? Through space. Okay. Same thing for free radicals. Now, why is a tertiary carbanion the least stable? Because of the same reasons, okay? Hyperconjugation and induction stabilize positive things. They destabilize negative things because you're pushing electron density in. You can't tell the alkyl group, by the way, don't do that now, okay? That's its nature. So it's going to push electron density through the bonds, okay? You can't make it not do it, okay? Okay, these are 2 reaction coordinate diagrams. Okay, and I'm probably going to go back to them here in a minute. But the first one is one of the propagation steps in bromination. Okay, so you've got this is Br dot. Can you see that there's a dot there? What is that thing doing? There, I'll make it big. Okay, that free radical, what does it do when it sees propane? It removes a hydrogen. It's called hydrogen abstraction. It's abstracting the hydrogen. It's removing it. Okay, so that's where the HBr is coming from. Okay, when you look at the propane molecule, do you see that there are two possibilities? We can take one off the ends, or we can take one in the middle. Two possibilities, okay? If you take one off the end, you would make this primary free radical. If you take one off the middle, you would make this green one down here that has a red electron. That's a secondary free radical. Okay, which one does it prefer? I know you know. The secondary one, because the secondary one is lower in energy. Okay, this difference, what is this thing called up here? When you're at the top of the mountain, transition state. This transition state between the two are different in energy by 9 kilojoules. Okay, so it's easier for the molecule to follow the green path than to follow the blue line. Okay, all right, over here is chlorination. Okay, so here we have the same thing where the chlorine free radical is going to remove a hydrogen from the propane. Okay, this is one of your propagation steps. You can get the secondary free radical or the primary. The secondary is still more stable, but notice what's different. Do you see that they're kind of opposite each other? This one, the step is endothermic. In this case, the step is exothermic. Okay, so at the end of this step, you're lower in energy. And you see that the difference between the transition states in chlorination is only 4 kilojoules. Here it's more than double in bromination. Remember, bromination is more selective. Okay, chlorination is not very selective. 4 isn't a very big difference at all. Okay, now, do you see that when these things are drawn? Let me just do one. Okay. Okay, here I drew it pretty much in the middle. Okay, well, what they figured out is that it isn't necessarily in the middle. Okay, and so if you look at this one, the transition state is closer to that intermediate free radical. Here, the transition state is closer to the starting materials. You see that? It's a little difference. Okay, here I drew it right in the middle as much as I could. Okay, so how do you know if it's closer to the starting materials or closer to the products? That is what is referred to as the Hammond Postulate. I kept wanting to say Hampton. I'm like, no, Hammond Postulate. If species are closer in energy, they're also more similar in structure. And that's how come, I'm going to go back, okay? That's how come this is more similar in structure to this. So they draw the transition state over to the right more. Here, it's closer in energy to here, the transition state. So they draw it over to the left, okay? And I tend to make my double daggers like this. Do you notice that they make theirs like that? I don't know. I don't think it matters, I guess. That must be the font they had. That's what I figured. All right, so the structure of the transition state resembles the species that it is closest to in energy. Remember, we're talking about pulling off a hydrogen, okay? So the CH bond is breaking, the HBr bond is forming, okay? So you're somewhere in between. Well, are they going to break and form it exactly the same? No, because they're different, okay? If it were the exact same atoms doing it, then maybe they'd be closer. But so one bond is going to be forming a little more than the other one. If it's an endothermic step, the transition state resembles the product of that step. If it's an exothermic step, the transition state resembles the reactant of that step. Okay, so if you look at that picture that we just had, notice that this is an endothermic step. The transition state more closely resembles the products of that step. This is an exothermic step. The transition state more closely resembles the starting materials. Okay, you see how that fits together. Are we going to worry? We're not going to worry exactly about where they are. Okay, somebody probably does, but it ain't going to be us. All right, the last thing we need to review is order of reaction. Okay, do you remember doing that? Here's a rate law. Rate equals K times the concentration of A. What is K? It's a rate constant. And sometimes you figure those out. Like you probably did. We're not going to do that. But sometimes you figure those out, okay? So here's a reaction. A plus B gives AB, okay? If the reaction rate is only dependent on the concentration of A, so that means that if you double A, what happens to the rate? It doubles. If you double B, what happens to the rate? None, okay? Because B is not in your rate law. The only way you can figure that out is by doing experiments and measuring it, okay? All right, so the order of the reaction is 1. How do you get that? What is the superscript of that? It's 1, okay? So if you have this one, if you find out that if you double A, the rate doubles, and if you double B, the rate doubles, okay? Then you have a 1 here and a 1 here, and 1 plus 1 is 2, so that's why the order is 2. Okay, now this one down here, the reaction is only dependent on A, but when you change A, it doesn't just double, okay? If you double A, the rate goes up by 4, okay? So that means that it's squared. Notice that the rate of the reaction is 2. Okay? I haven't ever seen any organic reactions that were like, aha. You know those weird ones? Yeah. That's inorganic. Yeah. Because I've never seen that. Okay? So ours are basically going to be 1 or 2. Okay? Okay? And we're going to talk about this. We'll say, what is the rate? What is the order of the reaction? And what is the rate law? Okay? But all we're going to do is write that. We ain't going to calculate out K or nothing. Okay? So if you like doing that, I'm sorry. You can ask Jay-Z. Maybe he can do a lab with that.
Can you go back?
Go back to this one?
Yeah, so we're just writing it down.
Oh, you don't have it?
No.
Oh, well, okay. That makes up for the other one. I didn't realize. I don't go through and like double check all that, so. Okay, now I'm gonna start chapter 5. Who printed out the slides? It's okay, you don't have. Might help you out, but it's okay. You don't need them because I'm gonna show you stuff, okay? Chapter 5 is called stereochemistry, one of your favorite topics already. Okay, I know. Okay, so I got 2 compounds here. Okay, well, what is it? If green is chlorine, what is this called? Name it. How many? I don't know. You can't tell? There's 4. Okay, 4. Okay, so the 2 compounds are 2-chlorobutane. Okay. Okay. These 2 compounds are dead. Oh, have a look at them. I'm gonna do my magic. Okay. They look pretty identical, don't they? Okay. But what you'll notice is that if I'm going to match them up, okay, So I matched up all the carbons, right? And look what didn't match up. The chlorine and the hydrogen. Okay, well, maybe I didn't do it right. Let's try a different way. Okay, so I'll match up the chlorine and the hydrogen. Do you see that I've got a methyl and an ethyl, and a methyl and an ethyl? They don't match up. This is called superimposing. Okay, when you try to match them up. Okay, so here are, this is isopropyl alcohol. Okay, and you'll notice that when I match this one up, everything matched. Okay, the OH, the H, the methyl, and the methyl, they all matched up. Okay, so you see the difference. These molecules are superimposable, and these two are not. Okay, there is a scientist by the name of Louis Pasteur. Have you heard of Louis Pasteur? I hope so. Okay, I would be very sad if you said no. All right, so because he's done amazing things. He's a brilliant man. He was working with tartaric acid, which I'll show you later on, that structure. But tartaric acid is formed in winemaking. Okay, they used to make a whole lot more wine in their own homes than they do now. And he was, well, they did. Okay, so he's looking at him and he said, oh my gosh, this crystal is the mirror image of that crystal. Do you see that these two things are mirror images? And he sat there with the tweezers and he separated them into two piles. Is that not amazing? Now, people have tried to reproduce that experiment and been unable. Somehow he got really big crystals, and a magnifying glass was big enough to do it. I mean, they weren't like little salt. They were big crystals, okay? And he was able to separate them and found out that they were both tartaric acid, but they did one thing differently, okay? They rotated plain polarized light in opposite directions. I'm gonna write that up here. Plain polarized. Now, why did he even think to look at it? Okay, I have no idea. Okay, so when you see light in the room, the light is going everywhere. Okay, anybody ever wear polarizing sunglasses? Okay, what that does is it only allows the light in one plane to go through. That's plain polarized light. Okay, so there is an instrument that you can use that makes light, and then you have a filter that it goes through, and that polarizes it, so you only get the light traveling in one plane. Okay, you put your molecule in there, and it will rotate the light one direction or the other, and we're talking 360 degrees around a circle. Okay, so if you rotate it clockwise or counterclockwise, okay, one of these rotates it clockwise and one rotates it counterclockwise. Off the top of my head, I don't know which is which. I know other things, but I don't know that. Okay. So, what?
At least you're honest.
Yeah, at least I'm honest. Because the only way you know that is to take this and put it in a polarimeter and run it. Now, somebody's done it with this one, and someone's done it with this one. They will rotate it the same amount of degrees, okay, but opposite directions. So one will go to clockwise and one will go counterclockwise. Okay, and you could look this up in a book and find it. Okay, the other reason I don't know, because you can look it up in a book. Okay, so what if you put this in a polarimeter? It doesn't rotate plain polarized light any direction. Yeah.
So, like, when you're talking about the two models of line,
Uh-huh.
I don't really understand, because if they're all single bonds, how can they not rotate around that?
They can, but they're still not the same, because even if you start rotating things, you can't get everything to match up. It's because this carbon What is special about this carbon?
It has a chlorine.
It has a chlorine, it has a
Hydrogen.
and it has a ethyl. Okay? All the groups are different. Here we have an OH and a hydrogen and two methyls. Two things are the same. Okay? When two things are the same, there is what in your molecule? A plane of symmetry. See, there's a plane of symmetry in your molecule. This molecule does not have a plane of symmetry. If I cut through the chlorine and the hydrogen in that carbon, well, what do I have on this side? A methyl, and on this side I have an ethyl. Okay, so what we're going to be talking about is molecules that have carbons that have 4 different groups attached to it. Okay, 4 different groups attached to it. Okay, so you're going to have to be able to find those. Okay, so I'm going to draw a molecule up here, and then when we do the slides, we're going to repeat this again a little. Okay. Okay, so find me a carbon up there that has 4 different groups attached to it. Okay, if you need to, draw in all of the all right, you got them all? Did I miss any? All right, is there a carbon up there? Which one? The one that the chlorine's attached to. Okay, usually we put an asterisk by it. Okay, that's usually how it's designated in structures, with an asterisk. Okay, is there any more? Can you have more than one? Why not?
Yeah.
Sure you can. You can have a buttload of them. Okay? Okay. Has anyone heard of L-amino acids?
Yeah, it's the type
Kind
of,
of
it's
works.
a-
And D-amino acids. Okay? Those are the 2 stereoisomers. Yes. Okay? And I'm going to okay? Do you see the chiral center? That's an amino acid. See how it got its name? Okay. This is our chiral center. We are chiral beings. We use L-amino acids. I'll explain L and D, but we have to get there. Okay? We use L-amino acids, and what sugars do we use? Anybody know? We use the D sugars. Okay? Bacteria use the opposite. So guess how we kill them? By inhibiting their synthesis. Okay? With drugs that won't hurt our synthesis, because we are chiral beings. Okay? So the new word of the day is chiral. Okay. I was taught to say chiral, but I've heard other people say, well, so-and-so says chiral. I've never heard that. Like, really? Okay. I've also heard someone say, well, somebody says corral. And I'm like, I don't know. I learned chiral, so I'm sticking with it. Okay. Yeah.
Like Cairo.
Yeah, but it's spelled different. Yeah. Okay. Chiral. Chiral means no plane of symmetry. Okay, no plane of symmetry. There are, if you take the outside of your body, we have a plane of symmetry, don't we? If you take the inside of your body, is there a plane of symmetry in there? It's not, is it? Okay, so we're chiral down in there too. Okay, oh my gosh. Okay, so but on the molecular level, we're super chiral. Okay, lots of chirality. Okay, so what is a protein made up of? Amino acids all put together. Okay, every one of those amino acids except one has a chiral center. So if you have 100 and they're all in the sink, you have 100 chiral centers. Okay, if you're an enzyme, you're made up of amino acids that have chiral centers. Which the amino acid that doesn't have a chiral center?
Is it glycine?
Yeah, it's glycine. Yeah, because the R would be an H. That's glycine. Okay, but all the other ones have a chiral center. And we do use a couple of these too. It's kind of rare, but I learned about that in grade school. Okay, so that gets you an introduction. Print those slides out on Monday and you'll get all the definitions. Okay. Okay, that says key. Okay, Caitlin.
I was last time.
I know, you get to be first.
Because I fell down the stairs.
Okay, Alexis Vince. Jessica.
Because I fell down the stairs.
Laisha.
I fell down the stairs. And then I landed on Cassidy.
Cassidy.
Oh, dang.
Step on your fingers.
Tyler.
I may go to this little room over here. I'll let you.
Madison.
No.
Gotta get the.
I told you that I was
Morgan.
no, I barely got up this morning.
Tiffany.
Right here.
Tiffany.
Yeah, or last week's one.
Glenna. No Glenna.
What is it? I gotta do last week's run and last week's last one.
Kaylee.
I didn't finish it. I didn't get the weight around. I didn't finish it. Well, I
Benicia.
we got a 0. On what?
Andrea.
On 11. She said if it's late, I won't put on.
Savannah.
That's
She's not here today, was she?
Yeah, there's only one week staying there like a weekend
Okay. Taylor.
Taylor, Tyler.
Skylar.
Thank you.
Brandon. Anybody want to claim it? What? It's Augusta. What was the only one that I had a Scantron for? Lakeland.
Thank you.
There's yours. Jeremy?
Thank you.
And how it comes on to yours. Yeah, she was sick. Brianna? Oh. Lindsay? Gosh, I'm running out. Abby? Abby. And Alexis. And Katie.
Thank you.
Dr. Wiseman, are you busy after this? I had a question about like.
I usually go to lunch,
Okay.
but I'll be back and I'll be here all afternoon.
I have lab. What about tomorrow?
Tomorrow I have class 9:30 to 12:15.
Okay.
So tomorrow afternoon I'm around.
Okay.
Yeah.
Awesome.
Yeah, I'm in here.
Okay. Sounds good.
Whoops.